Hello everyone, I'm Jingyao from Tsinghua University. Today I will talk about our recent work, FollowUpAR, enabling follow-up effects in mobile AR applications. This work is working with my collaborator Guoxuan, Danyang, Qian, and under supervision of Professor Zheng Yang. Augmented reality enhances the real world by rendering virtual effects on users' field of view. Nowadays, AR has provided immersive experience in entertainment, education, healthcare, and even in industrial production. There are also some well-known AR solutions such as Google AR Core and Apple AR Kit. They allow a user to select an anchor object and attach related virtual effects on it. For instance, when a user selects a dragon, a virtual flame will be attached to the dragon's mouth. And similar, in a ruler application on the iPhone, we can also attach some measurements on a cube. AR Core and AR Kit are able to continuously check the motion of the smartphone to adjust the effect. For example, as seen in the demo, when we move the iPhone slowly and keep the cubic stationary, the virtual measurement result will change its location and orientation. However, once we change the location of these anchor objects, the virtual effects will misalignment and hence the whole view is distorted. For instance, the virtual flame and measurements do not follow the dragon and the cube's motion. In a nutshell, today's mobile AR solutions lack the ability to render follow-up effects to moving objects. So why existing mobile AR solutions cannot render follow-up effects? Let's dig into the system architecture of AR Core. The AR Core is equipped with three key capabilities, including the camera motion tracking, the plane or anchor detection, and environmental understanding. Let's focus on the plane or anchor detection. It allows smartphones to find the suitable place to render the virtual effects. However, the core issue is that they assume anchors of surface are static and lack the ability to check the 6 degree of freedom pose of them. Hence, they cannot render follow-up effects to them. In a nutshell, we think the pose tracking of anchors is key to further bridge the gap between the virtuality and reality. Note that in our work, the object's pose is a combination of its location and orientation. So next, let's take a glance at how existing works track the object's 6 degree of freedom pose. First, some works leverage the expensive and sophisticated sensors of devices. For example, the Microsoft HoloLens are equipped with 4 different types of cameras. However, these expensive sensors are not simultaneously available on commercial smartphones. And second, classical visual feature matching based objects pose tracking. However, the cumulative drift and low precision leads to the virtual effects misalignment. Third, deep learning-based methods. Although the performance of these solutions meets the demands of the AR applications, these approaches require complete pre-modeling of specific objects and pre-training of neural networks in advance. They can neither track arbitrary objects nor run on phones in real time. So in summary, none of previous solutions can be used on smartphones in ubiquitous scenarios. In this work, our goal is to track objects pose in real time on commercial smartphones without pre-training. Furthermore, let's recall the system architecture of AR Core. FollowUpAR provides AR Core with the anchor pose tracking function and eventually enable smartphones to render follow-up virtual effects. The running demo of FollowUpAR from a Google Pixel 4 is shown in the above video. So how FollowUpAR can provide such an excellent AR experience? We find that today's commercial smartphones are equipped with sensors capable of generating sparse point clouds. For example, the Google Pixel 4 is equipped with millimeter wave radar for gesture recognition, and iPhone is also equipped with laser radar for enhancing AR experience. So our key insight is that can we leverage these relative sparse sensing measurements and fuse them with visual techniques to check objects 6 degree of them pose? Let's think about the rationale behind the effective fusion. The 6 degree of freedom pose can be decoupled as normal translation, tangential translation, rotation, and scale. Among these 4 tasks, the camera and radar have their individual advantages. For example, it is difficult for a monocular camera to measure depth, but the depth can be easily occurred by a ranging radar. In contrast, as for the tangential direction, The vision-based solutions will accurately check objects by pixel or feature points matching solutions. Further, the vision-based solutions can check the object's rotation. However, radar-based solutions sometimes merely treat the whole object as a reflector. Hence, it is hard for them to calculate the object's rotation. But compared with radar, the vision-based solutions cannot occur the absolute scale of the object's motion. For instance, they do not know how much distance a pixel change in an image represents the distance in the world. All in all, we can find that camera and radar have their individual but complementary advantages. So our vision is that fusion would overcome the weakness of each sensor and accurately check the object's pose. Based on our key insight and vision, we designed FollowUpAR. From top view, FollowUpAR provides AR core with the anchor pose tracking function to check object's 6 degree of freedom pose. Let's dive inside. The FollowUpAR consists of 3 key components: the millimeter wave radar tracking module, the camera tracking module, and the fusion framework. Although the system architecture seems clear and simple, realizing this design is non-trivial. 2 major challenges we need to address. First, how to check the object's pose, and more important, we also need to answer where the checking result error comes from and how to profile its distribution. The modeling of the error distribution actually influences the precision bottleneck. And second, how to fuse this heterogeneous state. So in what following, let's introduce how FollowUpAR overcome these 2 challenges and realize pose-checking of objects. We first introduce how millimeter wave radar estimates objects' motion and how to profile its error distribution. FollowUpAR calculate the distance as well as the direction vector n from radar to objects using the millimeter wave FMCW signals. Specifically, the distance can be calculated by applying the range fast Fourier transform operation on the intermediate frequency signal. And the direction vector n can be obtained by resolving the multiple angle of arrivals. Existing works generally assume the radar error follows a normal distribution. So is it the truth? If we don't solve the problem, the following optimization on fusion framework will aim at wrong goals. Hence, in FollowUpAR, we analyze the error distribution of the millimeter wave radar from a down-to-top perspective. And we propose the physical level radar error distribution module. The physical level radar error distribution module considers 3 essential components of the errors: the thermal noise, the signal adaptive wide Gaussian noise, and frequency sampling error. For more details about the formulation derivation, please refer to our paper. As for the camera tracking module, we design a feature point matching based optimization framework. The illustration of the concept is shown in the figure. We also set the optimization goals of vision-based tracking as minimizing the reprojection errors. Similarly, in FollowUpAR, we also perform the least square optimization to minimize the reprojection errors. Further, let's introduce how to fuse about 2 tracking modules. Before presenting our fusion solution, let's recall our key. Although it is straightforward to realize that fusion would overcome the weakness of each sensor. However, after rethinking the characteristic of each module, we find that unlike visual features in terms of precision, scale, and density, the sparse point clouds have a relatively low spatial resolution. Simply using traditional feature frameworks such as the classical Kalman filter or particle filter will not achieve better performance. So in FollowUpAR, we choose a different way. Instead of simply using a fusion framework, we treat the fusion task as a joint optimization problem and leverage a factor graph to optimize the final pose of the object. Let's take a look at the factor graph-based joint pose optimization framework. The whole optimizations include 2 parallel tasks: the tracking optimization module and the modeling optimization module. The former is to report the object's pose in real time according to the camera and radar tracking modules. It includes the short-term interframe tracking and the long-term local pose tracking. And the later one is leveraged to maintain the object's 3D models for long-term and accurate tracking. With a high-quality generated point clouds, the tracking quality will also be promoted. We only illustrate the core components here. For more mathematical details, please refer to our paper. We implement FollowUpAR on a Google Pixel 4. We conduct experiments in a laboratory and a crowded office with different illumination intensities and background motions. We further compare our FollowUpAR with 3 related systems, including a classical visual feature matching-based algorithm, which takes RGBD data as input, and 2 learning-based state-of-art solutions. However, these 2 methods need complex pre-training. The evaluation result shows that FollowUpAR achieves an average translation accuracy of 3 millimeter and an average rotation accuracy of 2.6 degree, outperforms the RGBD-based ICP and the learning-based NOCS by more than 30%. And the performance is also comparable to the state-of-the-art learning-based solutions post-RBPF. However, among the related works, only FollowUpAR can check object pose in real time on smartphones without any pre-training or pre-modeling. And we further illustrate a couple of random examples of FollowUpAR, which indicates the 3 millimeter translation error and 2 degree rotation error, and ICP, which 7 millimeter translation error and 6 degree rotation error. As seen, with the increased tracking results, errors for merely 5 millimeter translation and 4 degrees rotation error, the orientation and position of the virtual flame are gradually misalignment, which leaves users with the impression of distortion. We further experimentally analyze some core components of FollowUpAR. According to the experiments, we found that first, fusing radar and vision is better than merely using individual of them. And our proposed physical level radar error distribution model performs better in the post-tracking tasks. Compared with simply treating radar errors as a Gaussian distribution, the physical level radar error distribution model brings about 20% system performance lift. And the proposed factor graph-based joint post-optimization framework outperforms Kalman filter, extended Kalman filter, and particle filter by more than 15%. This outstanding performance, on the one hand, is due to the leverage of factor graph. On the other hand, lies in our theoretical derivation of error distribution from radar and camera tracking models. So let's summary. The contributions our work lies in 3-fold. First, we propose FollowUpAR, the first 6 degrees of freedom object pose tracking on smartphones in real time and without complete pre-training or pre-modeling. And from our technical novelty, we designed the physical level radar error distribution model to push the limit of millimeter wave radar sensing accuracy, and design a factor graph-based post-optimization framework to fuse heterogeneous states with diverse spatial resolution. We also implement FollowUpAR on commercial smartphones. That's all. Thank you. If you want more details about our work, please refer to our paper.